Greetings. Welcome to Tracking Pandemics. This is Module 2.1, Reproduction and Transmission. There are several pressing questions that we try to answer, both during an outbreak and in its aftermath. One of those questions is how likely an infection is to spread or move among individuals in a population. This characteristic of an outbreak is called transmission, and it's affected by a great number of factors, including environmental conditions, host behavior, pathogen biology, and more. One way we can begin to address transmission is to calculate the prevalence of an infection. This is the number of infected individuals at any point in time. Prevalence is an instantaneous measure of spread. One benefit is that it's fairly intuitive. Unfortunately, it's not exceptionally useful for predicting what a pathogen is going to do. We can also calculate incidence, which is the rate of new cases over time, usually normalized to some standard number of susceptible individuals. Unlike prevalence, incidence can be used to determine risk. Both of these numbers tell us the frequency of infections in a population. We can also calculate a number called secondary attack rate. This is the proportion of infected individuals among susceptible individuals in close contact with a primary case. So, for example, if we have a household in which one person of the household becomes infected, we can calculate how many other individuals in that household that are susceptible to the infection are likely to be infected. We have secondary attack rates for many infections. For example, measles has an 80% secondary attack rate, which means 8 out of 10 of those susceptible close contacts are likely to be infected with measles. Monkeypox, for example, has a much lower secondary attack rate of 5%. The drawbacks to this secondary attack rate, although it's fairly straightforward and intuitive and easy to calculate, it depends heavily on the definition of close contact. In this example of a household, close contact may be fairly straightforward. In other, what are called congregate populations, such as nursing homes or prisons, we can fairly well define what a close contact may be. However, in a lot of environments, this is not possible. For example, on a university campus, especially an open campus, where there is significant flow between buildings into the campus population and out of the population, it becomes much more difficult. Secondary attack rate also requires that we identify the primary case, and in some infections, this is more difficult than in others. So prevalence and incidence and secondary attack rate are useful in particular contexts to describe the frequency of infections, but none of these numbers measure actual transmission. That is, how likely an infection is to spread among different populations. This is a crucial number. If we can accurately determine the transmission rate of an infection, we can begin to consider predicting the movement of that infection into the near future. This is crucial for building accurate models that can then go on to inform effective and timely public health responses. So a fairly common method for measuring the transmission or spread of a pathogen is one that you're probably familiar with more now than you might have been in the past. This is a number called R. R is essentially a way to determine how rapidly a pathogen reproduces or replicates. For some pathogens, we can calculate this in a laboratory setting, but this is often not fast enough. Too artificial, reproducing in a lab is not the same as reproducing out in nature. Or in some cases, it's not even possible, as many pathogens are unculturable. So for most infections, we end up estimating R in a real-world setting. In order to do that, we measure the average number of secondary infections that arise from a single infected individual. If we assume that our entire population is susceptible to infection, this number is termed the basic reproduction number, also called R0 or R0. Calculating R allows us to estimate how quickly an infection is spreading or will spread among a population. Higher R0 means a faster transmission. Good data is at the heart of making R as useful as possible. First of all, we need to know how many people come in contact with an infected individual, called contact tracing. Second, we need to know when the index case was infected. And third, we need a reliable estimate of the infectious period of the pathogen. In the early stages of a novel infection, such as SARS, determining a value for R0 allows us to predict how quickly an infection will spread. It is only during the early stages of an infection, though, that the assumption of 100% susceptibility is largely met. Again, intuitively, a higher value of R0 means a faster spread. We'll return to this underlying assumption in just a minute. So quantitatively, we can use R0 to calculate what is called the projected incidence. In other words, the predicted number of new cases that will occur at any particular time. We'll call that time I sub t. This is simply the number of cases at the previous time point, we'll call that I sub t minus 1, multiplied by R0, the number of people each of those cases will, on average, infect. Remember that we are looking at average. R0 is an average number of individuals infected by an index case. For example, if there's one case yesterday, we'll call yesterday day 0, and we know our R0 is 3, we can predict the number of new cases today, or day 1, to be 1 multiplied by 3, or 3. Tomorrow at day 2, it will be 3 multiplied by 3, or 9. Here in this graph, I've plotted the projected incidence for various values of R0 over the span of about 3 weeks. If we look at an R0 of 3, which is the light blue dots on this graph, we can see that in 1 week or 7 days, our R0, at an R0 of 3, our projected incidence will have become over 2,000 from a single case at day 0. In 2 weeks, 1 case at an R0 of 3 will have become 4.7 million cases. I've also plotted various other R0 values. These come from estimates of R for actual infections. R0 of 3 corresponds roughly to what we consider COVID's R0 to be. R0 of 15 is more similar to what measles is. In general, any infection where R0 is greater than 1 means that infection is going to spread within a population. Any R0 less than 1 means the infection will peter out. So we have a distinct boundary line here. I've shown it as a gray line where R0 equals 1. R0 equals 1 means on average one person will infect one other person. And essentially you will have a flat line. It's important to consider that there are a lot of infections where the R0 is below 1. We generally don't hear much about these because they don't spread very far, even within what would be considered a 100% susceptible population. A second thing to consider is how easily we can see a small change to the value of R can cause a significant change in the trajectory of an infection. As a result, even infections with an R0 below 1 are important to monitor. These represent potential emerging infections that with a small change may quickly make the jump from sub 1 to greater than 1. In other words, from a dissipating infection in humans to an infection that will spread. Finally, there is a very important assumption that underlines this analysis. The calculation of R0 assumes unconstrained growth, or a population that is 100% susceptible, and there are no barriers to the spread of this infection. These barriers may include immunity, but could also, even early in infection, include things such as geographic isolation, social distancing, either imposed or natural, adverse weather conditions, adverse for the pathogen that is, and others. So while R0 is often valid for the very early stages of infection, where it's localized around a particular focus, it quickly becomes invalid in the real world. If we take measles for an example, has an R0 of 15, and we project this out, assuming a time step of 1 day, measles would infect all humans on the globe within about 10 days. We know, of course, that this does not happen in reality. So R0 is a valuable estimate of theoretical spread of an infection and can be useful on the ground in the very early stages of an outbreak. But unfortunately, R0 is not nearly as valuable in the real world as a predictor of spread. So we need a better number. A corollary to R0 is called the effective reproduction number, sometimes seen just as an R. You may also see it as R sub E, RT, or even RN, net reproduction number. And the difference here is that R is the average number of secondary infections arising from infected individual in which some individuals are already immune. For example, these icons in yellow are already immune and cannot pass that infection along. And hopefully it's easy to see how the calculation of R, or estimation of R, more closely follows what happens in a real infection compared to the calculation of R0. So how do we estimate R, or RT? Well, one very simple way is to calculate it as a function of R0. Namely, RT is R naught times the fraction of your population that is susceptible to the infection. For example, at time 0, the susceptible fraction is 100%. In other words, 100% of your population can be infected. In this case, RT is simply equal to R naught. Here I've plotted a very theoretical relationship between susceptible fraction of population down here, or what we call S, and the effective R, or RT. Okay, as time progresses, as you can see at different values of R, as time progresses, the susceptible fraction of your population drops from 1 on down, and the value of RT likewise drops. The rate at which it drops depends on how quickly a population becomes less susceptible. Again, we avoid saying immune to a pathogen because it's not simply immunity that can cause a decrease in susceptibility. So one key feature of RT is that it changes with changes in your population. This is in direct contrast to R naught, which is a basic fundamental characteristic of a pathogen that does not change. Theoretically then, what we need to do in order to stop the spread of an infection is to move enough people, enough individuals in our population into the S box. Sorry, out of the S box. As we make fewer and fewer people susceptible, our effective R will drop. Eventually, if our effective R drops below 1, the infection will dissipate. In reality, it's much more nuanced. Individuals can move into and out of the S box. For example, if an individual is infected and becomes subsequently immune to a pathogen, that immunity may last for a certain period of time, at which point that individual may become susceptible again. This can happen even if a pathogen does not change or a new strain of a pathogen does not emerge. Immunity is known to wane in particular cases. In addition, something we don't think too much about on a daily basis, but somewhere around 4 million babies are born in the United States alone every year. Most of those babies arrive as susceptible to many of the pathogens that are currently circulating. On the other end, as individuals get older, they may become more or less susceptible to pathogens as a result. Individuals may gain weight or lose weight. They may move to new places where they encounter pathogens they've never encountered before. There are many, often subtle, often difficult to assess factors that can affect the value of S, or the susceptible fraction of our population. And that makes this equation, while relatively intuitive and certainly easy to calculate, difficult to get good estimates in order to make a valid calculation. This model has the advantage of being simple, and it illustrates the underlying relationship between RT, R naught, S. But we need a very good way to calculate or estimate S before this becomes a useful model. In the next module, we'll introduce a related concept called herd immunity, and we'll discuss how we use public health data to estimate S in ways that are more useful on the ground. Thank you.